finite difference is a method for approximating a derivative. Finite differences can be derived using an expansion of a Taylor series, or you can do it graphically, which is the approach we're going to use here. Given some function f of x, if we wish to know the derivative of that function, we can use fundamental definition from calculus that the derivative is the change in y over the change in x. So we'll evaluate the function at 2 points, x0 and x1. That corresponds to the function at x0 and the function at x1. Now we write change in y over change in x, and that is function at x1 minus the function at x0 over x1 minus x0. In finite difference notation, it's common to simplify the function evaluated at x1 as f1 and the function at x0 at f0. It's also common, instead of writing x1 minus x0, just to simply write delta x. And it's implied that delta x spacing is the same as the spacing used in the x evaluating the function at x0 and x1. This formula is commonly called the forward difference, and is written like this: the forward difference of the function at f0 is equal to the function evaluated at x1 minus the function evaluated at x0 over the change in x. See, graphically, we're approximating the derivative at 0 as a straight line where the derivative comes from looking at a point in front of the point of interest x0. Similarly, we could evaluate the derivative of the function at x0 by using a backward difference. In this case, we look at the value of the function behind x0, and so the formula becomes f0 minus f minus 1 over delta x. This is the backward difference. The backwards difference is especially useful when you're doing real-time data processing and you're trying to approximate a derivative, because at the current time you don't know what will happen in the future, and so in order to approximate the derivative you can only use points that happened in the past or the backward difference. We can get a more accurate estimation of the derivative at a given point by essentially averaging the slope between the forward and the backward difference. So to do that, we're going to take a difference that's twice the width, and the formula becomes the derivative at x0 is equal to the function evaluated at x1 minus the function evaluated at x minus 1 over, and now the width is 2 delta x. This is called the central difference. The central difference is the preferred derivative to use if you have the option of doing it, because it's more accurate. Again, you could go back and look at the Taylor series expansion and see where this comes from to verify that indeed it's a more accurate first derivative. We can derive higher order derivatives by using the lower order derivatives. So here is the forward difference, and let's take the second order forward difference, taking the derivative of the function evaluated at x1 minus the derivative of the function evaluated at x0 divided by delta x. Graphically, we're defining the second derivative as the change in the first derivative divided by the change in x. The first derivative can be approximated using a forward difference at x1, shown here with the double lines. The first derivative at x0 can be approximated using the derivative shown here, which is a single line. Following through with the math, we write the finite difference approximation for the derivative at x1. We write the finite difference approximation for the derivative at x0 and do the algebra, and we're left with the formula for the finite difference approximation for the second derivative using a forward difference. You can use the same approach to calculate the backward difference. We're looking at approximating the derivatives behind x0. Using a similar procedure as we did for the second order forward difference, you can come up with the second order backwards difference. To find the central difference version of the second derivative, we can use the same procedure. Here I've written the derivative of the first derivative for central difference, and then we can find the central difference for each of these derivatives. In orange is the central difference about f1, and in red is the equation for the central difference about f minus 1. So the second derivative in the central difference is f2 minus 2f0 plus f minus 2 over 4 delta x squared. This turns out to be not very convenient because it requires such a wide range of data. If you want to find the second derivative about f0, you need to know 2 data points back and 2 data points forward. Another way to calculate the central difference for a second derivative is to use half steps. In this case, I want to calculate the second order derivative about x0. So I'm going to use a half step as noted here, x1 half. The central difference about x0 is f1 half minus f minus 1 half over 2, and then the delta x is 1 half delta x. And that gives me a central difference about f0, and then I'm going to take the derivative of both of those to get the second derivative. And now take the derivative of each of these. So I want the derivative at f of 1 half and the derivative at f minus 1 half, and I'm going to use central differences. So following through and calculating the central difference about f minus 1 half and using a half of delta x as my step, and also doing it for f of minus 1 half, I have the following equation, and I simplify. That gives me. So in summary, here are the first and second order derivatives for forward, backward, and central difference. One common application of finite differences is to solve differential equations. I'm going to explain how to do this by an example. So here's a first order differential equation. The first step is to replace all the derivatives with their appropriate finite differences. For simplicity, I'm going to use a forward difference on this one. Here I've copied the propagation equation, which we found from substituting the finite difference approximations into the original differential equation. And I've also written down the initial conditions. You need initial conditions if you're going to propagate the equation. You also need initial conditions even if you're going to solve the original differential equation. I've also picked a value for delta t, in this case 0.1. It's a side note, the choice of delta t can be important. If you pick a delta t that's too large, then you won't have enough accuracy and you won't get a good representation of the solution to the differential equation. If you pick a delta t that's too small, you can end up with a solution that ends up being unstable just because of a numerical round off. So let's propagate. I now can calculate the value for x1. That is 10 minus 2 x0, which is 0, times delta t, which is 0.1, plus x0, which is 0. The answer is 1. So to keep track, I've drawn a little graph down here. X of 0 is 0. Now x of 1 delta t is 1. Substitute. We can now propagate this further by just renumbering the propagation equation. So I've renumbered here by shifting all of the numbers up by 1. You should feel comfortable doing this. If you look back at the derivation, you should realize that the particular indices that you use don't matter. All that matters is their numerical value with respect to each other. So this says if I know at 0.0, I can get 0.1. This says if I know 0.1, I can get 0.2. I'm now going to substitute values in, and the value is 1.8. So I'll draw 1.8, and now I just continue, and I'm going to write down a couple of values for you. And so the values for the next 2 points are shown here, and if you were to continue this, you would find that you end up with a curve that looks something like what I've shown in green. It's a increasing exponential, and if you remember your differential equations, you should remember that a first order differential equation has an exponential decaying or an exponential growing curve depending on the initial conditions and the forcing function. For review, here's the procedure for solving a differential equation using the finite difference method. The first step is to substitute a finite difference approximation for each of the derivatives into the differential equation. In the example shown, it was a simple first order differential equation. If you have a second order differential equation, you'll need to substitute in approximations for the second derivative and for the first derivative. If it's a third order, then you'll need to go and look up the finite difference approximations for higher derivatives. The second step is to solve the resulting equation for the highest index. In our case, we looked for the x with the largest subscript. This is our notation. So we're solving for the value of the dependent variable that is furthest along the curve, that is furthest out with respect to the independent variable. In our case, that was x1. The next is to apply the initial conditions, and this will give you the first step in the propagation. If the differential equation is second order, you should expect 2 initial conditions, third order, 3 initial conditions, and so on. If you're using central differences, you may find that you have to make some assumptions about the initial conditions. Part of applying the initial conditions also means making some choice for delta t, delta x, whatever the independent variable is. Again, this may require some trial and error. Final step is to propagate the solution. Use the propagation equation to find the next value of the solution and then feed that back in, and you can march along the solution curve as long as you need to find the approximate solution for the function, which is the solution to the differential equation.